Ladies and gentlemen, boys and girls, I'm Alan Willison, and it's my pleasure to welcome you to this meeting of the Hertford Astronomy Group. We've got a really exciting evening for you tonight. We've got 4 students from the University of Hertfordshire who are going to be presenting some talks on astronomy. The format of the evening is, first of all, to say a big welcome to Ben Birmingham, who has organised our speakers for the evening. Ben is an associate professor at the University of Hertfordshire, if I've read his CV correctly. And I'd also like to say a big thank you to the students who've come along tonight, to Callum, to Shravya, to Matt, and to Niall. We've got some really good talks, which should last between about 10 or 15 minutes each, and there will be a short time for questions afterwards. Now, bearing in mind that we've got 4 speakers this evening, I'm going to ask if we can limit the number of questions to 4 per speaker. And if we make that 2 from the Zoom area and 2 from the floor area in the university, then we will know where we are and we should be able to finish in a reasonable time, and also to be fair to our speakers. Those of you in Zoom land, if you wish to send a question along, pop it into the chat box and send it along, and Steve, hopefully at the other end, will read it out at the end of the talk. Steve's also got a roving microphone this time, so if people in the lecture theatre want to ask a question, give somebody a chance to get up to you with the microphone, and hopefully we will all hear what it is. Okay, so the format of the evening will be that in a few moments I will pass over to Ben, who will introduce our speakers. We will run through the speakers, and following that will be just a few closing remarks from myself to be able to thank everybody who's come along and give you a few messages about the next meetings which are coming up. So that's enough from me, and I'm now going to hand you over to Ben at the university.
As Alan said, I'm an associate professor here at the University of Hertfordshire in the Centre for Astrophysics Research, and it's my pleasure to bring with me 4 of our PhD students who are going to talk to you tonight. First up is Callum Morris, who did his undergraduate here at Hertfordshire before going to do a master's down at the University of Sussex, and is now back here doing his PhD on cataclysmic variables and things related to variable stars with a supervisor named Professor Phil Lucas, who some of you may have bumped into at the open nights and things like that. So come along, Callum, and take it away.
Okay, hi everyone. So I'm here to talk to you about, the star known as UGPSJ 194310 plus 183851.8. I've cut the title for you. We have renamed it something more reasonable for the rest of the talk. It is a cataclysmic variable, as we say, with novel character, because monthly notice of the Royal Astronomical Society won't let you say new without double and triple checking everything. So we're going to structure this as a way to describe the benefits of multi-wavelength imagery and multi-method astronomy, because we've thrown the kitchen sink at this one particular object. So without further ado, I will take it away. So a quick guide. So we're going to first how we discovered what we're going to call source 363, because that's its catalogue number from a smaller subset. We're going to give you a brief overview of the UGPS survey that it was found in. And then I'm going to kind of give you a brief intro to near-infrared astronomy, because I don't know how much some of you already know about it, because obviously it's not quite as easy to get hold of infrared stuff as it is the optical stuff. And then I'm going to give a quick sort of chat about the benefits of multi-wavelength astronomy for classification purposes, because things do different things in different wavelengths. And then I have a brief interlude about telescopes, because that's what you guys all mostly love. So I'll give you a talk about some of the really big stuff I got to use. And then a quick overview on what actually is a cataclysmic variable for those of you who don't know, if you're not really into variable stars. So here we go. So first, I want to quickly chat about source 363. Now, this was discovered with short period variability in the near infrared. Now, UGPS, as I'll mention in a little bit, has widely spaced 3-year imaging. So the fact that how do we manage to find a short period variable in there? Well, initially, we didn't think we had. See, it was originally published as a star with what we call negative or blue colors, i.e. it was more blue, essentially for an infrared star, it was brighter in J and H than it was in K, which is what most of the images are in. This seemed very strange, but when you encounter the fact that these large telescopes take a long time to switch filters, it became a more plausible idea that in the time taken to switch from the K to the J band filter on the United Kingdom Infrared Telescope in Mauna Kea, the star had actually changed in brightness, which caused these weird colors. And that obviously bothered. We should probably follow that up with stuff, but getting hold of time for one object is challenging. But we did notice that the IFAS, which is a survey that uses, it's a narrowband survey, so you get blue light in the optical as well as H alpha. I'm sure you guys have access to H alpha filters on your telescopes. And it showed a 1.1 mag H alpha excess, which is huge. So something very high energy was going on in this system. That, combined with 15-minute circa variability, leads us to assume that there's some sort of compact binary system, but we don't know of what type without further investigation. So for those of you who don't know what UGPS is, why would you? It was using this giant telescope here. It's a 4 meter on Mauna Kea. And it's now sadly defunct because the government stopped sending it money. Wipe tears away. I know, it's still raw. And it basically covered 1,868 square degrees of the northern sky, focusing on the galactic plane, but also some of the northern sky above it, as an additional kind of addendum to 2MASS as well. And you got 2 epochs with it, which was a big change to 2MASS. You can't find variable stars if you only have one picture. Whereas at the 2, you can see some of the large scale changes, but not short period stuff. Or so we thought, at least. Now, a huge number of stars in this sample were variables, and there were 618 that had even more, well, more than one magnitude of variability, which is pretty big. Now of these, some previous work by Phil, Lucas, and his previous PhD student, Carlos, who he still calls me sometimes when he forgets who's who, they found that the majority of these are young stellar objects, or protostars, call them what you will, basically stars that haven't yet turned into proper stars. They're still feeding from their birth environment. But there were still a large number that were other types of infrared variable star, and quite a few of these completely just this huge classification. I've been working on all of these 11 particularly weird stars. I think I've sussed them all out now, minus one that has been continually hard to work out. But certainly 363 was like the hardest one to do, so that's the one I thought I'd stake my flag in when I started my PhD and try and work out what it is. 4 years later, we've got the answer. So astronomy in the near infrared, for those of you who don't know, basically this lovely image from James Webb, handily came out a few days ago, so I've chucked that straight in. Then it shows the benefits nice and easily. We've got the visible light spectrum of Barnard 33 there, and next to it we've got the near infrared from WST. And you can see, the handy thing is, you can start to see through that gas and dust that gets in the way, essentially the optical extinction. You can start to see through it because you're now probing cooler emission, so colder light that's coming from different sources. And this is quite penetrative, so it can get through gas clouds a little bit easier, which is great for looking for dusty objects, as well as looking for embedded sources and other things like that. In the case of source 363, it is because it is hidden in a disk. So we'll start off with our first of our multi-wavelengths. So we found it in the near infrared. Getting infrared time for a spectrum is really, really challenging. And if it was what we thought it was, that probably wouldn't tell us all that much that we wanted to know, because if it is a compact object, they're not normally doing stuff in the infrared. The infrared doesn't contain too many emission lines that will help really prove a point, but the optical does. So an optical spectrum here with SOAR, if anyone's heard of that, it's a 4 meter class, or 4.1, had to go a little bit and brew in the nice round numbers. It's in Chile, up on Cerro, I've written it down later, a big mountain in Spanish. Terrapantron, thank you, Ben. And this was using the Goodman spectrograph, which has been upgraded, so we got some upgrade director's time on it. One of Phil's mates, basically. As you can see here, we're seeing these huge emission spikes. Now these are from ionized hydrogen and helium. Now that implies that there's a lot of high energy activity going on, and it's mostly associated with something called mass transfer. So that is when you take, when you have a heavy star, and that is using either gravitational strength or magnetic fields to take mass from another companion star and feed it onto itself. And upon doing so, when it hits the surface of a star, it releases a lot of energy, and that energy release ionizes materials, which is what we're seeing in that spectrum. And we also managed to get some more experimental time. The amount of things that we managed to get without doing an honest-to-God telescope proposal was quite impressive. This is using PFQHY, which is a CMOS rather than a CCD that they bolted onto the William Herschel telescope on La Palma, and they were looking for rapid cadence variables to test it on. And we had one that kind of filled all the boxes, so I sent it their way, and a few days later, these came back. We have a U, or U prime, because it's using Sloan filters, but U prime and R prime, so basically just U and R filters as you know them already. Light curves, each one 90 minutes long. And as you can see, we're seeing similar behavior with some subtle differences in these kind of curves. But we can't tell actually what's going on. We just know it's going up and then coming down again. And for cataclysmic variables, you need to find periods, either the orbital period for the two stars going around each other, or the white dwarf spin period, so just 1 day on the white dwarf. And to use this, now you can get super long exposures by doing proper telescope proposals, but no one would give us any. Did eventually, but we had to find other methods of using that. And Niall's going to talk about this in more detail because he developed an amazing machine learning AI tool to basically do it all for us without having to put any effort in, except the long hours he put into typing it up. I basically just go, Niall, can you make it work? Yes. Now, when we first tried to publish this with just 2 cycles, it's not good enough to test, but it came up with a number called 63 minutes. That's where it looked at those and went, that is definitely periodic, and it's 63 minutes. Now, Munras were having none of it, but nonetheless, we got a light curve from the Liverpool telescope, also on La Palma, 2-meter class, and we got 5 hours. Well, technically we got 10 hours, they just haven't done the other 5 yet. This came through 2 weeks ago. So this is brand new data of the, well, press, as it were. And as you can see, it's the lower light curve there. And if we say, let's test it with 63 minutes as a period, we can basically phase fold it, which, if those of you who don't already know what phase folding is, we basically just divide each point on the light curve by where it is within a given predicted period, so that if something was halfway through the light curve, we would put it halfway through repeatedly every time it comes up. And that is the plot above. As you can see, 63 minutes basically fits. They're never perfect cataclysmic variables because there's so many factors going on. So big score number 1 for the machine learning code, and a specific finger to the referee who turned it down in the first place. I'm still not bitter, I swear. Now, we also we still need more for cataclysmic variables, so X-rays it was. So I politely asked NASA if they'd use the Niels-Gerels Swift Observatory, which is a combined X-ray, gamma ray, and UV space telescope. Kind of does the lot. It's brilliant. And got some time on it. And as you can see here, the upper image is a U-band backing in gray and black. And then in the kind of blue is photon counting from X-rays. So individual X-ray particles that have hit the detector, and they're centered in that red circle, and that red circle is where our star is. So we know that our star is an X-ray emitter. And X-ray emission plus ionized material and a period the way it is says this is a cataclysmic variable of a specific type. So yay, mystery kind of solved. So whilst we celebrate solving the mystery, here are some stats on the telescopes that we used. If you're interested, so at the top, there's SOAR. These are the nicest, most artsy pictures I could find of each of the particular telescopes. I took that one, WHT, from the INT, because it was daytime and there's not a lot to do when I'm standing at the Isaac Newton telescope in the day. So exercise some non-astrophotography skills. Now, so WHT is a 4.2 meter telescope. SOAR is 4.1. Liverpool is just a 2 meter, but it's fully robotic. It's brilliant. It's actually run from John Moores University up in Liverpool. And you basically just send them some coordinates. And if they like your work and you manage to write a proposal properly, they will go and observe your stuff for you. It can be used for everything. It's got a spectrograph on board. It does technically do infrared and optical at the same time, which is wonderful. Although the infrared instrument has been broken since my last run on the Liverpool telescope. Actually, it broke halfway through my data collection, and it's never been mended since. If anyone asked, it wasn't me. I wasn't there. We also have Swift, which is the old one out. It's a space telescope. It's got the UV camera is not brilliant. It's only 30 centimeters. A lot of you probably have bigger telescopes than that yourselves. But it's just basically for, obviously you don't need to be that big in space anyway, but it's basically for pathfinding to help pinpoint if there is a UV source where you're seeing your X-ray photons come from, because if you're getting one, you should be getting the other as well. So it's basically a useful double check tool. It can also give you light curves. In our case, it didn't give us anything useful because they took weird imaging cycles with it. Apparently they were troubleshooting at the time. But if you've got any questions about these, feel free to ask me at the end. So a quick introduction to categorical variables for those who don't know the specifics of them. Basically, what you have is a white dwarf, which is basically the gravitationally condensed core of a normal mass star after it's done being nuclear fusion, lots of condensed carbon, neon, and oxygen. And in this case, it's in a close orbit binary with a red dwarf. So these are main sequence stars that are on the low mass end, probably about 0.1 to 0.2 solar mass for categorical variables. There are similar things called symbiotes that Niall will talk about in a bit. That is just where you change the red dwarf for a red giant. No other change. The physics is still the same, and there's still a dichotomy in types. You see, we break these kind of CVs into polars and intermediate polars. And that is solely based upon how far apart they're orbiting and thus how they accrete matter. Closer orbit ones, the polars, will use magnetic fields only, so their sheer magnetic strength is enough to tear material from the red dwarf onto its surface and then ionize the material. And that is quickly seen in the lower spectrum. You see the one that's marked P. They tend to have a much brighter emission features, and they also do have double peaked lines. So they have two spikes as opposed to one singular one. We don't see that in our spectra, so ours isn't a polar. But we also know that this intermediate polar spectrum doesn't really look the same as the one I showed you earlier, which is strange because it should do. Ours should be intermediate polar. So we have to raise a question as to why exactly is ours different? Well, here's a nice little handy little plot I made. I'm not showing you the entire population of IPs in this because, well, I actually couldn't write all the references down because there were about 200 stars of the red variety. But we've got all of the what we call short period IPs. This is a small subgroup they're called short period IPs, weirdly, because they have a long spin period. They have a short orbital period, but you discover them solely based upon their long spin period. Don't ask me who named it. Well, actually, I do. It's Mukai, wonderful guy, but on the naming system there. Now, the green box is source 363. Now, we've got quite a wide box around it. That's the error bars for the orbital period. We know that we have a set limit on where it can go based upon how bright the star is. We know its distance. It's about 900 parsecs away. And if we know its distance and we know its magnitude, we know how big the companion is, and then we can put constraints on the orbital period. So we know it must be within those areas. And if it's there, it's in a very, very tiny group of, well, really, 4 other similar objects. The 2 other lower blue stars, there's question marks about their actual membership of this group. Now, it's worth noting that ours is also very different when you look at its behavior in multi-wavelength space. Ours is a very red object, with all the others are very blue. They're bright in the optical, not in the infrared, which means ours stands alone, which is pretty damn interesting, I think. Yeah. So from final concluding remarks from me, multiple wavelengths and multiple methods is if you've got a strange variable star and you need to work out what it is, throw the kitchen sink at it. Every telescope you can get your grubby mitts on, try it to work out exactly what's going on, because you need to have everything at once to not only find out what something is, but also if something doesn't really match, you need to know why it doesn't match. Infrared selection finds interesting new variables. These are IPs, category variables. They are optical variable stars. They are not normally found in the infrared. In this case, it's because we have a very thick disk, we think, so lots of matter being accreted onto it, which is making it basically re-emit in the infrared, which is strange, rare, and thus far the only one we found, because I've not bothered to look for more yet. It's on the to-do list. And the final point I wanted to make is machine learning is a sophisticated new tool that can be used to really speed up observational time for these kind of objects that you need a long time to observe normally. If you can do 2 cycles and then put it into some code, you've saved yourself 5 more hours on a telescope that can be then spent doing more science. Right, if you want to read about it, there's a paper there. Type it into Google. You can read it for free on Munras or Archive if you're feeling interested and you want the less Cliff Notes version of this work. Right, any questions? Oh.
Thank you. On one of the slides with the Swift telescope.
Swift. There you are.
Two green sources.
Now these are, I should explain this in a bit more detail, sorry. Now the color bar represents the amount of photons that hit the detector in a specific place, but would then trace back to the single start point. So we have those yellow points where we have 3 photons from that particular area. If we're doing very low number counts, X-rays are finicky things to observe, but you don't expect large number counts for these sort of quite distant infrared sources. But there's, within our kind of ring of confidence ring, we had about 30 X-ray photons, which is way more than the X-ray background. The X-ray background at this distance that we're looking through, because it's the galactic plane, so most of it doesn't get through, is about 2, so 28 more than the background is pretty decent.
I was kind of curious as to whether the two sources were your binary or whether that's just a coincidental similar source.
That's just because of the resolution on Swift.
Okay.
We did apply for some time with a much bigger X-ray telescope, XMM, but we basically wanted to tweak our proposal for the next time through to get a better look at it. So hopefully some more X-ray data will be available then.
The black image is the
UV is the UVOT is not again, this is only a 30cm telescope, so UVOT also doesn't help matters. But this is the best way I could find to put the X-ray and the UV all together. Oh.
The binary, what angle were you looking at? The edgeways on or straight down? And had it been the other way, I'll start again, yeah.
Were you looking at this sideways on, so they were spinning towards you, or were you looking sort of down at the poles? If it had been the other way, would it have made the discovery easier or harder?
In the infrared, harder. We think we're looking at them edge on, just because if the disk is fairly, we obviously don't have too much of a knowledge on this. We use much more high-res spectroscopy for that. That is very difficult to get because it's veiled by the disk. So this is pretty thick. But if we're looking mostly at that, we know it should be roughly edge on, but with less degree of certainty than you usually would have for these sources. If it was sideways on, it probably would have been a bit more challenging because it would have been less infrared bright. And that's how we discovered it in the first place, was through the infrared selection. Although maybe discovered by optical selection instead. Who knows?
Thank you. Okay, so the question from Jeff Bryant is, what is the timescale for the phase of life and what is the end result for the 2 stars?
Oh, okay, great question. So the timescale for these is on the order of around about 1 million years. It can depend on the orbital separation and the overall masses of the white dwarf and the companion. We think we've got a pretty heavy white dwarf, something on the close to the white dwarf mass limit, the Chandrasekhar limit, so 1.4 solar mass-ish. So it should be able to last quite a while. The end result, it can be a bit dependent. You can go for a supernova type 1A, depending on exactly how efficient the accretion is from the red dwarf, but not guaranteed. But otherwise, you'll basically will just end up with the 2 stars failing in their binary orbit, and they'll just drift apart. Or they could carry on with this until the material's all used up. We think because our white dwarf is heavy, it's more likely to go the 1A angle, but not enough to prove anything.
Thank you.
Okay. All right. Anything else, or am I done? Disconnect.
So next up is Shravya Shenoy. Shravya did her
Masters in Leiden and is now in her first year of a PhD here, working with colleague Dan Smith on stuff to do with the LOFAR survey, I think. Yes, yeah, the LOFAR, which is a big, very low frequency radio survey that we have a leading role in at Hertfordshire. So anyway.
Okay, perfect. Thank you, Ben. My name is Shravya Shenoy, and I'm a first-year PhD student at the University of Hertfordshire. Thank you for being here today. So I don't have very many results today because I just started my PhD, but I will give you an introduction to radio astronomy and why it's really useful. Which brings me to the layout of my talk, where first I will be talking about extragalactic radio signals and who discovered it for the first time. and why radio astronomy is useful. And finally, a little bit about my PhD project, where I use radio observations to understand how stars form in galaxies. Let's start with the electromagnetic spectrum, which is basically what I'm assuming a lot of you have already seen. It's just light at different frequencies. The one we're most used to is the visible light, which is what we use to see and make sense of the world. But there's also light at other frequencies which we cannot see with our naked eye, but we use them. For example, the microwave, where we heat our food, or X-rays to detect fractures in our bones. But today, I will specifically be talking about radio waves. Now, as you can see, when it comes to visible light, the wavelength, or the distance between one end to the other end of the wave, is really small, of the order of microorganisms. But when it comes to radio waves, they can be as long as meters, as long as buildings, for example. And within radio frequencies, we also have different bands which are used for different purposes. So on the lower frequency side, you have these waves used for maritime radio navigation stuff. But as we move towards higher frequencies, we have the one that most of us are used to is the megahertz frequencies, which is used to connect to radio stations to listen to music, for example, or at the higher end, which we use for radio astronomy. Now that's about radio waves. Let's talk astronomy. As a field itself, it's been around for centuries, but you'd be surprised that radio astronomy only started in about 1930s, when Carl Jansky, this distinguished gentleman here, was hired by Bell Laboratories in the US to basically try and build an antenna to see what are the sources of static, because that was the time where they were developing transatlantic communication. And he built this array, which basically had wheels, so you could point it in different directions, and hence the name merry-go-round antenna. And he classified these static into 3 different categories. One was where you have nearby weather disruptions, such as thunderstorms, one where you have faraway thunderstorms, and the third one was this faint hiss, which he noticed in every part of the sky that he pointed to. And he got in touch with his astronomer friend, and they tried to figure out the source of this radio sound. And they thought it's probably coming from the sun, but when he moved the antenna away from the sun, he continued to hear this faint hiss. So what they did later is realize that it was coming from one particular region of the sky near the Sagittarius constellation. And they concluded that it's probably high energy electrons in that region which are emitting radio waves. And that's what he observed using his antenna. Now, the problem is he didn't quite continue to work on it, which is unlucky for us, because Bell Laboratories didn't fund him because it didn't really impact their transatlantic communication. And astronomers at that time had no idea how radio astronomy worked, or if it was even worth it. So he didn't really work on it. And this is an image I'm sure a lot of you have already seen, one of the first images of the black hole, but this is the image of Sagittarius A star, which is the black hole at the center of our Milky Way galaxy. And this is a radio image. And this is around the same area where Carl Jansky first detected that hiss. But the one person who continued to work on using radio observations was Groth-Reber. He was basically an electrician by profession, but he was an amateur astronomer, not unlike some of you here in this room. What he did was he used this big parabolic dish in his backyard, and he wanted to make maps of the sky using radio frequencies. Now, at that time, this was in Illinois in the US. People didn't really know what this was. Some of them thought maybe his rainwater harvesting. Some of them thought it's used for communication, probably. But he used this dish to try and make a map of the sky using radio frequencies. In fact, if you go to NRAO in Green Bank in West Virginia, you can still see a reconstructed version of his telescope today. So this is the map that he tried to make, where he basically pointed his antenna and found what the radio strength was coming from those regions of the sky and made a sort of contour map. And it's very interesting because it was for the first time that sources like Cassiopeia and Cygnus were observed using radio frequencies. And this was around the time of the Second World War, where he was probably one of the only radio astronomers in the world who was still actively working. And he was an amateur astronomer. And the advantage of using radio astronomy is, for example, if you look at this image of Cygnus A, this is in the optical regime, which a lot of you use to look at the sky. But by using radio telescopes, you actually see these beautiful plumes coming out of these galaxies, which if you use normal cameras which are sensitive to optical wavelengths, you would never be able to see these jets coming out of those galaxies. So that's one of the coolest reasons why I got into astronomy and radio astronomy in particular, because it makes these galaxies, it shows that these galaxies have a reach much beyond what we see in the optical regime. Coming to Jocelyn Bell, now she was one of the first people who actually who looked at transients, and she noticed that there were these blips in the radio spectra coming from this source. And at that time, a lot of people thought this is probably aliens trying to contact us, which is why they also nicknamed this source LGM1, or Little Green Men 1. But unfortunately, it wasn't aliens, and they found that it was pulsars. Now, pulsars had been theoretically predicted to exist, but it was the first ever time that it was observed. And this was done using radio frequencies. And some of you might know, but pulsars, if this works, well, it doesn't. So pulsars basically have these jets coming from the poles, and they kind of act like lighthouses, where if the jet is pointed in your direction, you have this frequency in the radio regime. When it's not, you don't see anything, which is what these blips are. So you can basically use these blips to try and estimate the rotational velocity of these pulsars. And to motivate why radio astronomy is really cool is that when you look at, for example, visible light and ultraviolet light, the Earth's atmosphere blocks out a lot of it. Whereas when you look at the radio regime, the Earth's atmosphere is almost transparent because they're long wavelengths. So they're not as easily scattered. So dust and gases don't really affect these radio waves coming to the Earth's surface. So we can build relatively cost-effective radio telescopes on the ground to actually observe these galaxies. And making radio observations, which was basically popularized in movies like Contact, is not quite how it works. So we don't really put on our headphones and try and listen to radio signals coming from space. And as much as I love this movie, Jodie Foster needs to move away from the array because the electronics in her laptop can actually cause interference. In fact, there's another fun story from the Parkes Observatory, which was in my title slide, where they saw these weird signals coming from time to time, and they assumed it's probably thunderstorms, until they very recently realized it's just because some people would leave the microwave oven doors open. And that was what was causing these interference. So even the cars that go there don't really have spark plugs anymore. They need to have glow plugs. So that's how sensitive some of these telescopes are. But in my work, I basically look at low frequencies like Ben mentioned. So I'm looking at 150 megahertz. Now, if you look at this image, you wouldn't think that it's actually a telescope, but it is. It's the low frequency array, which is mainly located in the Netherlands, but we have stations all across Europe. And for example, in the UK, you have one in Chilbolton. So we have these arrays which combine the data and try and look at these extragalactic sources using radio waves. And my work basically looks at star-forming regions of the galaxy. So what you're seeing on the image here, the left one, is optical image, or the H alpha, or the hydrogen emissions from this galaxy. Now, hydrogen is basically, it basically comes from star-forming regions because massive stars emit a lot of H alpha. But what's really cool is using radio data, we can also probe similar regions of the galaxy. Now, this is interesting because for faraway galaxies where the light gets dimmed by the time they get to the Earth's surface in the visible and UV light regime, the radio observations are still really good. So we can use radio observations to probe these faraway galaxies. Now, this looks really nice on paper, but stars don't quite emit a lot of radio emission. So it's a convoluted way in the sense that when these massive stars go off as supernovae, they have shocks and they excite the medium around it. And these excited electrons, or cosmic ray electrons, when they move in the magnetic field of the galaxy, they emit synchrotron emission, which is basically just radio emission. So in a long way, in a convoluted sense, we can use radio observations to trace star formation in galaxies. That was the image. This is a plot which Dan Smith made in 2021, which is basically radioluminosity, or how bright a galaxy is in the radio regime, as a function of the star formation rate, which means the quantity of stars forming in a galaxy. And this is really promising because even at low frequencies, the brighter a galaxy is in the radio regime, the more number of stars it is forming. So we can use the radio brightness to estimate the quantity of stars galaxies are forming. And that brings me to my summary, which is basically that radio frequencies are much less affected by dust and clouds compared to other wavelengths, shorter wavelengths. And in my work, we understood star formation in galaxies using radio observations. And in general, radio astronomy is cool. So I may not have a lot of results, but I hope you found this interesting. Thank you.
Any questions?
Go on, I'll be brave again. On the image that had the that one, are the red regions indications of more dense areas of star formations or more dense, bigger stars?
That's a good point. So the thing is, in star forming galaxies, we also have something known as an active galactic nuclei in the center. So it could, and these emit a lot of radio emission. So in this case, it's hard to isolate star forming regions from the active galactic nuclei. We do have some techniques where we try to minimize the influence of active galactic nuclei, but in the central regions, it means really bright in radio emissions.
Out of dots.
Those are star forming regions, yeah. Or more specifically, supernovae regions.
Thank you. You said that you're in the first year of your PhD, so I'd like to ask, what are you hoping to lead up to in the sense of information and the results of your research?
The existential crisis. No, but what I hope to learn is try and see galaxies farther away using radio observations. And we have something really new, which the telescope called VIV, where it basically looks at tiny regions of galaxies specifically, but that's in the optical regime. So my project mainly tries to combine to look at smaller regions of individual galaxies using the optical emission as well as radio, and try and see how they compare, because different processes in astronomy emit light at different wavelengths. So when you look at radio images versus optical images, you can try and see what processes are happening in those galaxies and what regions it's happening in. Thank you.
Good evening. If you're looking at something that's multi-light years away, are you looking back in time?
Yes. Yes. That's the short answer of it, which is really funny because when I talk to people about things that we're looking far away, or things that we're looking far away in time in terms of redshift, people usually get confused, but yes, we look back in time. So we look at galaxies, how they were forming billions of years ago.
Put a mirror on it, the reflection would show us in the Stone Age.
Or if you were in another galaxy, you'd be seeing dinosaurs when you look at it. Yeah.
We have one more question on Zoom, which is what radio observatories will you be mainly be using for the source of the data for your studies? That's from Jeffrey Bryant.
Thank you. That's a good question. I'll mostly be using data from LOFAR, which is a low frequency array. So you have these stations in different countries, but we process them and use combined interferometric data from LOFAR.
Tell us why there are so many in the Netherlands.
Because that's where it initially started, and you have these local stations. So it also depends on what arc-second resolution you're looking at. So depending on that, you can use longer baselines or you can use local stations. That's a good question. Thank you.
Thanks, Javier. So next up is Maddie. Sorry, Matt. Sorry, it's not Maddie. It was going to be Maddie. Maddie has more hair. So this is Matt. Matt did his MPhils in Sussex and has come to Hertfordshire to do his PhD, and he's working with Jim Geach on galaxy formation and structure and lensing and stuff like that. High redshift stuff. Highish.
So yeah, so Ben's just introduced me. I said I did my undergrad at Sussex, MPhys, and I've now gone from Shravya, who's a first year, to me, who is now a fifth year, just about to finish writing up. So I'm going to talk a bit about gravitational lensing. So I've put here cosmic telescopes, so understanding distant galaxies using gravitational lensing. Ooh, where did I do it this way? Okay, so a brief outline. So I'm going to be go a bit into what gravitational lensing is, and then talk about the specific type of galaxies I work on, which are called sub-millimeter galaxies, which are sort of high redshift starbursts, so very distant galaxies. I'm then going to talk a bit about ALMA, which I don't think I'm wrong here. I think it's objectively the best observatory. There may be some disagreement, but they are wrong. And then I'm going to sort of talk about the source I look at, which is a single lensed galaxy. So I call it 9I09, which I'll tell you why that name is there in a bit. But in the literature, it has a few different ones. But yeah, I'll just keep going on. So what is gravitational lensing? Sorry, I'm rubbing my beard there. So gravitational lensing is, just as the name suggests, it's like a lens. But what you have is you have a background galaxy, and then some intermediate, maybe a galaxy cluster or an individual big galaxy, and that bends the light around it. And then you sort of see it in your telescope, often as a ring or an arc on the sky. So what this does is it basically magnifies it, both in terms of flux. So I say they're about, so typically for galaxy sort of lenses, it's about a factor of 10 brighter than what you would expect, and also does scales to a similar amount. So what this allows us to do is sort of do studies on objects on scales which you wouldn't otherwise be able to get apart from in the nearby universe. So you may have seen this image here. So this is one of the first JWST images that were released. And so this is of the SMACs, I think it's 02723, which is just some coordinate numbers at the end. And what you can see there is at the center, you've got all of these sort of blobs. This is a big galaxy cluster. And you can also see a lot of the wispy features around there, so sort of lines. And I've heard some people refer to this one up there, sort of an orange one. Looks a bit like Donald Trump's hair. So yeah, so they're all the wispy bits are all lenses. And so while I've not looked at this data in particular, there's a lot of wealth of information there. And while the galaxy cluster is quite a bit of distance, the lenses behind are really high redshift. Some could be sort of incredibly high. I don't want to guess there. So there's a close up there, and you can see the one I set up there, and then all of these wispy lines down here. So what about sub-millimeter galaxies, which are the specific class which I work on? So sub-millimeter galaxies, astronomers aren't very imaginative with their names. So sub-millimeter just comes from the wavelengths when they were first observed. So these are incredibly starbursty galaxies, often sort of having star formation rates. So they're forming stars at hundreds or thousands of the Milky Way. So incredibly star forming. They tend to be optically faint. And this image on the right here is ARP 220. It's not, I say it's a nearby galaxy. It's still 260 million light years away. So as we said, looking in the past, this would be what the galaxy looked like 260 million years ago. And you can see the sort of dark region across sort of the center. That's dust. When stars form, a lot of young stars, the big ones start kicking up dust, and that blocks a lot of the visible light. So these objects tend to look very red. So you might think that means they're not forming stars, but in this case, it's the dust blocking all the blue light out and just letting some of the red light through. Unlike Callum, who showed the picture of Barnard 33, I think it was 33, so which is also known as the Horsehead Nebula. I'm more interested in the dust itself rather than trying to peer through it. So I don't know what's going on. But yes, so this population is the high redshift version, sub-millimeter. While they're incredibly rare, they do actually contribute to a significant fraction of star formation at that time of the universe. So I said they're high redshift. I thought I'd just add a brief slide about what redshift is. So as many of you may know, the universe is expanding, And as the universe expands, more distant objects are moving away faster than the nearby ones. And as an object moves away, the light gets stretched, and it gets stretched to look more red, hence the name redshift. And in the case of my galaxy, we're looking at a redshift around 2.5. So if you've got some really blue light at the start, this has gone off red, it would be in the infrared by the time it reaches us. So my work mainly focuses on using ALMA, which, as I said, is definitely the best observatory in the world. This picture's come out a bit darker on this here, but you can actually see the nice Milky Way sort of disk there in the background. And then you see all of the different antennas. I'm not sure how well you can see it back there, but ALMA consists of 66 separate antennae, and so 54 12-meter dishes and then 12 7-meter. So you can see the picture on the right. Basically, to get the different observations, you can move around the dishes to get different resolutions. And they basically just have one massive truck or two massive trucks, Otto and Law, which pick up the dishes and then move them around to whatever configuration they want at that time. So the interferometer, as it's known, is 5 kilometers up in the Atacama Desert. The reason behind this is, unlike radio, sub-millimeter is awful to do on ground level. So you need to go really up above the atmosphere, 5 kilometers up, and even then you still can get some issues. The main problem with the atmosphere is a molecule we could really do without, I reckon, which is water. It really ruins the images, so I would rather it just be gone. But yep. So now I want to go a bit more on to, sorry, is it? Yeah, sorry. So we'll just go on now to the source I work on, I said 909. So the interesting thing about 909, so many of you may have heard of Galaxy Zoo and sort of citizen science projects. So this was discovered first with Galaxy Zoo using the CFHT, or imaginative naming scheme, as you can see, the Canada, France, Hawaii telescope, and also VISTA. So what happened here was citizen scientists were given the opportunity to look at various images to try and see if they could identify lensed objects. And here's an image they were shown, sorry, I'm pointing down there, in the right here. So you can see you've got this yellowy object in the center, and then this red sort of ring, partial ring around the outside. So the volunteers are asked to look through and then see if they could flag it. And this was flagged very early on. So if any of you watched Stargazing Live, it was probably about almost a decade ago now. But this was observed live on air. And it was one of their, I think when they first announced it on the first day, this was already sort of picked out as a prime candidate within a few hours. So, as I said, part of the Galaxy Zoo, one bonus to that is you can get a lot of press every time you put a paper out. So Chris Lintott recently wrote sort of a thing on, I can't remember the name of the website now, the Sky at Night newsletter, which was about my paper, which is linked at the bottom. And also it was an article many years ago in the Daily Mail talking about the first person to identify it as a lens. And then it also means it's got its own Wikipedia page. So if I ever forget anything, I can go straight there and find out. I have actually gone there and found information where I wasn't sure. I'd heard it and I wasn't sure where I could find it. Went straight to Wikipedia and it gave me a reference. So that was great. But let's talk a bit about the source now. I just want to say a few little things about what we know about it. So I said a nearby galaxy was 260 million light years away. This is a redshift of 2.6, which means it's about 10 billion light years away. So fairly early in the universe. The universe is about 13, 14 billion years old. So this is very early on. The lensing means it's been magnified by about 15 times compared to what you would have normally seen. It seems to be, based on sort of analyzing some spectra, which I'm going into a bit more detail in a bit, to be an edge-on disk galaxy. And the star forming rate is about 1,000 times that of the Milky Way. So here's a few images of the source in a few different wavelengths. So you can see up here, this is the original VISTA image. It's very faint there. You can see a sort of smudge maybe on the outside. With the sort of lensing object in the center. You can see the lensing object here in the Hubble image. And then when you go to the radio up there and the far infrared or submillimeter, then you can sort of see the sort of ring around the outside is really bright and you lose the middle galaxy. The reason behind that is the middle galaxy is a big elliptical galaxy. So then typically known as red and dead. So in the optical, you can still see the old starlight and it'd be quite red. But in the submillimeter and the radio, there's not a lot going on to produce the radio emission. And in the submillimeter especially, which is dust emission, there's not been star formation for a long time. There's not much dust left in the system. So it's completely invisible in the far infrared. So the next slide I'm going to go on to is a bit about my own work. I apologize about the contours. You put them in academic papers, but they do ruin the images. But what you've got here is sort of the sort of continuum, what is known. So at all wavelengths, you've sort of got a background level from the system that it's just emitting at. And on the right-hand side are two nitrogen lines. These are sort of nitrogen, everyone's heard of it, but these can tell us some interesting things about the source. And this weird sort of shapes on the bottom. As I said, it's lensed. It doesn't tell you much about what the source looks like. So the way you get that out is you have to make a sort of sophisticated lens model and then pass it back through that to try and see what it looks like if it wasn't lensed. So that's what we've got here. You can see this data here is a bit noisy. That's, again, the problem with water in the atmosphere. And so that's what we've got there. So the next slide sort of shows what we can do with that. So the nitrogen lines, they're ionized. They're only found in ionized regions. So it can tell us more about the ionized gas in these systems, which are typically around sort of star-forming regions. So stars, they heat up the gas around them and ionize it, called H2 regions. And this is where these the doublet will be found emitting from. So the ratio of the two lines can tell us a bit about the density of the gas. So the density of the gas is sort of related like this curve here to the emission line. And you can see down the bottom there, we've got the Milky Way, and up there, 909, next to G333.6, etc. That's a star-forming region. So what we're finding is that the ionized gas is 10 times the density of the Milky Way, and at the same time comparable to a density of a star-forming region, but on scales of a whole galaxy. So now I want to go on to a bit more, I'll quickly run through this. So this is sort of my current work. So we managed to get 6 hours with ALMA to look at this source. And you can see the maps at the top correspond to a couple of the emission lines down there. I'll get onto that in a second. But you can see there's a wealth of different spectral lines in here. Water lines, carbon monoxide, cyanide. So a lot of poisonous gases as well as water again. But what they can tell us is sort of things like the hydrogen cyanide there, and cyanide can tell us about really dense gas in the regions. And sort of carbon monoxide is ubiquitous. It's that really big one, which I've cut off on the right-hand side. That's the one you typically see in non-lens sources. The rest of them, it would take days looking at it to even attempt to try and get any of these lines. So, as I said, you've got the HNC and CN there. They're very dense gas. One thing you may also notice is that a lot of the lines have got a similar profile. That's how we know it's an edge-on disk. So with higher resolution data, we can model the shape of the emission lines and then work out what it's doing. And it appears to be quite a big disk. And then again, this is the CO there. And you can see down there, we've got some fainter lines, which are, again, CO, but with isotopes of carbon. So carbon is normally 6 protons, 6 neutrons. 13 CO has got an extra neutron. And the other one there, which is C18O, is oxygen with a couple of extra neutrons. So just to close up now, I've said gravitational lensing, whilst rare, offers us sort of basically allows us to see a great opportunity to study distant objects in far greater detail than you would otherwise be capable of doing. They are a class of extreme star-forming galaxies, which are found in the very early universe. The galaxy I said 909 is one such object. So it's 1,000 times the star-forming rate of the Milky Way. And also spectra, which many of us use, as Callum spoke about earlier, can offer us a wealth of information about the conditions within these sort of sources. And thank you for listening. Has anyone got any questions?
There are two questions on Zoom. First question from Richard Shepherd. Do you think we would understand what we see of lens galaxies if we had no suggestion of space fabric being able to be warped and bend light?
So I think even at the time, so what would we know about lensed objects if we didn't know space could bend? So even at the time, so one of the first sort of confirmations of general relativity was the bending of light. You can sort of fudge it with Newton to get an idea, but I don't think people would have actually thought it was a real thing until we actually saw it. When they were first seen, people weren't actually sure if they were actually gravitational lenses or just some weird other effect. So even when we knew about general relativity and space-time bending, people still weren't convinced at the early days that they were lensed.
Another question, I think, on a similar subject from Jeffrey Brunt. How do you stop the delensing algorithm from being self-fulfilling? If you generate a lens model, that gives you the result you want or expect.
So the way you do the lens modeling is, I'll go back to the, sort of, just the image so we can. So you can see in the middle here, you've got this lensed galaxy here. So it's not just throw in the image and then hope for the best. So you model the system here. So you try and find information on the actual lensing object itself. So its size, its mass, and sort of mass distribution. So you model that itself. So in this case, we've modeled this one here and also its northern companion up there, smaller galaxy. So you model them and then just pass it through the lens model. And then to make sure it makes sense, you actually look at what the model predicts the lens to look like back through.
Any questions from the floor?
I was actually going to ask a question very similar to the last one, but it was also thinking of flipping it round. So I was thinking of the Donald Trump images you showed us. Could you use the rather bizarre shape of the lensed galaxy to analyze the shape or the structure of the galaxy that's doing the lensing?
Yes, so people do that. So one of the ideas I've been rejected now twice, so it's a bit sore, for ALMA observations on this. So one of the things you can do is go for very high resolution lens sources. And one of the things there is, well, you've got the visible light here as well. When you get to really high resolution, you can start to sort of probe the substructure within the actual lensing source itself. So yeah.
And our final speaker is Niall Miller. Niall did his undergraduate at Kent and his master's at Kent, working on something. Now he's doing his PhD here, also with Phil Lucas.
Yes, with Phil.
On variable stars.
Right, yes. So hello, I'm Niall. I'm going to talk about the VVV catalogue of periodic variable stars. This is probably the most nerdy talk today, so I apologize if this is really boring for some of you. I've tried to keep it as pretty pictures as possible, but stellar astronomers, generally speaking, we don't get nice pictures. It's just a star. It's not, we don't get nice nebulosity. But I will start with the interesting stuff, because we're all astronomers here, right? So let's talk about the telescopes first. So all of the data I use is from the Vista telescope in Chile. Here you can see it in its natural environment. Looks like Mars, but it's actually Chile. This is an infrared telescope of the 4-meter class. Here we can see some more information about it. The Vista telescope generated the VVV survey. The first V in that is Vista. Vista variables in Via Lactea, which is just Spanish for we use the Vista telescope to look at variable stars in the Milky Way. And you can see the blue outline here shows us the rough kind of survey area of the VVV survey. Now, the thing I kind of want to draw your attention to is 2 points. One, this is an infrared survey that is time-based. So we've got a lot of temporal information about a lot of stars we've just never seen before. And furthermore, we've got about 700 million stars. That is a lot of stars. That is a lot of stars. To get a little bit more nerdy about it, so I did say we had 50 to 80 epochs. This means that about 50 to 80 times we observed a region. Now, VVV is kind of funny because most of your amateur telescopes, you'll have just one chip on your camera, right? Just one CMOS, one CCD. Vista had 16 infrared detectors that had gaps in between them. So when we wanted to take a picture of space and we wanted it to be complete, we'd have to move the telescope slightly each time. This is really good because it means that every time we had a picture, we had multiple pictures per picture. That's why I say 50 to 80 epochs, but actually 100 to 400 observations, which is really cool. It gives us a lot of kind of flexibility as we're starting to mess with this data a bit more. This is the super nerdy way of explaining it, but basically if a star was here, it would have had 2 observations per observation. Kind of strange, but basically, again, a lot of data. And to hammer this home a little bit, I'm going to slowly zoom in on this purple point here. So this is the galactic bulge, which is kind of the bulk of the VVV survey. And I'm going to zoom in slowly at that part, because 700 million is not a number our monkey brains were made to comprehend at all. So I'm going to slowly zoom in. So this is pixelated, so I can't remember it, but it's, I think it's 5 degrees. This is now 1 degree, half a degree, quarter of a degree, 1 arc minute, if you're familiar. And focus more so on the fact that these dark points aren't really dark points. Zooming in a little bit more. And finally, again, we can see that there's a lot of stars here. I couldn't possibly analyze all of those. I'd love to. I analyzed about 200 and it took me an hour. So if I did all of them, all of the potentially variable stars, it would take me about 7 years. And unfortunately, no matter how much I cry to Phil, he won't fund me for that long. So I had to do something else. So you might think, well, how do we possibly analyze this much data in this shorter time? And as Callum has already alluded to, and is seeming to be our ever-present overlords, AI. The scary thing that is, well, it's a bit funny, but it's very, very useful. So what I did is I showed a neural network, an AI, a lot of periodic variable stars, and I showed it a lot of non-periodic variable stars, and I said, please learn the difference between those. And I got to the state where I could basically say, hello, Mr. AI, can you tell me if this star is periodic or not? And it would reply with no. Well, it doesn't actually reply with that. No, it gives me a number. We call this a false alarm probability. Basically, what's the chance that this star is periodic or not? So it said here, nope, I'm pretty sure that this star is not periodic. I'm 96.9% sure that this isn't periodic. Great, cool. Do it for the rest of them. And indeed, and it still works. So we can see, was this one periodic? And it was 99.4% sure that it was periodic. And when we look at it, indeed it was. Great, so it's done my job for me. So now we've got a very big catalog of reliable periodic stars. What can we do? This is where I kind of deviate from my research and don't just talk about the interesting stuff because I just keep doing the nerdy stuff of making those numbers better. But instead, we're going to start to like analyze what's actually there because, again, there's a lot of things that we've just not seen before, which is really, really cool. Retina warning. Oh, this is the paper, by the way, submitted earlier this week. Very nice, lovely, thank you. Yeah, retina warning is a little bit bright. But this is basically a pretty good classification or ish of the type of like the variable stars zoo, you might call it. And the thing that I think is most important about this is those 2 things at the top, extrinsic and intrinsic. Stars can vary for a plethora of reasons, like this is way too many. But you can categorize it into 2 things. Either the star's varying because something got in front of it and it appears to vary, or the star itself is doing something wibbly wobbly. Extrinsic, the easiest way to think about it is an eclipse, right? Every time we see an eclipse, the star gets dimmer and it appears to vary. Intrinsic, all sorts of weirdness, and we're going to get onto one of those now. AGB stars. I've labeled it as an AGB star. These actually are asymptotic giant branch stars. I cannot spell asymptotic, so it's AGB star. This is a really nice image of one taken by Alma. There you go, Matt. But pretty nifty way of showing the star because the reason the star is variable is it keeps losing mass. It's very old and it's dying and it's basically running out of fuel and it keeps doing these periodic cycles of ejecting mass is wrong. Callum told me this, but basically they keep losing things. And this is what they look like in very pretty pictures. But in my data, they look more like this, which is a little bit more boring. It gives me a very good way of explaining phase-folded light curves, as Callum has already done. So we can see here, this is just the brightness of the star over time, over about 10 years or so. Now, we can see by eye that this is clearly periodically variable, right? You can see that it's going up and down, up and down. It's not always this trivial, but this is a very good way of explaining it at the start. I run some fancy code, doesn't matter, mathsy, boring stuff. And it figured out that I think that this star is periodic once every 486 days. So if I draw a dotted line there, and then I fold that effectively every 486 days, we get this there. Lovely. And this is a very archetypal AGB star. AGB stars are very dramatic. They have very high changes in magnitude. This changes by 2 mag, and it does that every 486 days. And we can see as well, these are way over in the intrinsic side of things because the stars themselves are varying. And here's another one that's pretty nifty, I think. basically the same thing. My point is that it's dramatic. It's got a very high change in magnitude. And when we phase forward them, we get this lovely sinusoid. Great, so moving on, let's have a look at some of the other ones. So here's a scientific rendition of a binary star. Pretty nice, I think. This is what the light curves look like. Binaries are probably my favorite. I really, really like them, mostly because when you look at the light curve, it's kind of funky. It's not that nice sinusoid that we're expecting. There's these two dips. And this is really cool because we get a lot of physics just for free, just from looking at them. Like we can measure the difference between these dips and get differences in masses, and the period tells us how close and far away they are. Really, really nifty. And again, importantly, these are in the extrinsic part of things because the stars themselves needn't vary, although they sometimes do, and that just breaks my code. But when they don't, and they're nice and clean, we can see this nice clean variability here. And these are just two stars passing in front of each other, and they appear to be variable because of that. Here's another cool example of one, quite nice. You can see this is basically when the big star disappears, and then the little star disappears, and then the big star disappears, and it does that. I think it's quite interesting, though, that this is like, 10 years worth of data, and it's been doing this routinely once every 2 days for 10 years. It's kind of strange to think that, if you think in 2 days' time or in 1 day time, oh, wow, this star has changed this much currently in the universe, and it's going to keep doing it. And that's pretty cool. I put question marks here because these are going to appear a lot more, because the thing about VVV data is because it's so unique, we can't cross-check with anything. We're on our own, basically. So when I see something, I'm like, I think that's a binary. I don't know. Hopefully it is. Kind of looks like one because we can see these two little minima here. But it's also got this weird slopey pattern to it. I showed it to Callum earlier and he made a funny face, so I don't think it is anymore. But that's pretty nifty. Sometimes as well, binaries, they needn't be so far apart that they're not touching. They can actually contact. These are, well, contact binaries, very creatively named. Or sometimes they're named after the first star we saw of its kind. So these are sometimes called W Umas, because that's where they were first discovered. And this looks like a lot like the normal eclipsing binaries. And basically, the only reason I think it could be a contact is because the difference between these two is quite small. This is what I'm saying about how we can look at some temporal data and get quite a lot of physics just for free, which is pretty nifty. Anyway, moving on from binaries. Young stellar objects / YSOs / T Tauri / baby stars. These are variable for a gajillion different reasons. The environment is so chaotic that there's 1 in a million reasons why they vary. Every time I show my supervisor a light curve, if he doesn't know what it is, the knee-jerk reaction is, oh, it's probably a YSO, because who knows. There's a really nice ALMA image of a YSO, and you can see the remnant material that is either going to form effectively the solar system, the planets, or a lot of that material falls onto the star by accretion. Here's some really nice VLT images of them. I absolutely love this. This one is so nice. Look at that. Lovely. But one of the things that can happen is if material's falling onto the star, it can create a hotspot on that star. And as that star rotates, we see that hotspot come in and out of view. And that's exactly what we got here, probably, I hope. You can see I've had to add YSO in here because any self-respecting astronomer, as I've just really said, they vary for a gajillion different reasons. So YSO could be there, it could be an eclipse, could be an eruptive. Yeah, it could be in a lot of them, basically. So this one, I think, is most appropriate to say rotation, because this is the hot spot of that star coming in and out of view. Pretty nifty. Here's another one. The size of this, like the shape of it, you can see how this one's a bit more pointy and this one's a bit more sinusoidal. Can give you actually a lot of information about the size of that spot, or if it's migrating, or if something else is happening. But pretty cool. Again, question marks because I think it is. All of the other checks say it is, but I couldn't possibly tell you. And YSOs sometimes do this as well. Pretty nifty because we have no idea why. We used to think it was because the disk that was surrounding the YSO basically became unstable and collapsed onto the star. We now think there was a paper published earlier was it earlier this year? Okay, very recently, that actually a lot of the time when they do this, it's because something's flown by it and completely disrupted the system, and it's done that. And I have a few examples of those, which is really cool. Now, these aren't phase folded anymore. That's why the periodic was in brackets at the start. These are just the light curve over time. I've got 4 examples of these. And you can see the star just increases in brightness by a significant margin. That's from 16 to 17 to 15 mag. At least a mag in brightness. And they normally stay at this bright period for a very long time. The literature used to be that they stay at this bright period for about 100 years, but there's one that is doing it for about 10 years. So who knows? It's a very hotly debated thing, and it's a very easy way to start a fight in a conference, basically. But here, these are labeled. These are here. These are FU Orionis events, generally speaking, but again, industrial-sized grain of salt there. Pretty nifty, though. I quite like these ones. These are pretty cool things. Another type of thing is a dwarf nova. These are cataclysmic variables. Callum's already gone through these basically. The only difference that differentiates, dwarf nova, polars, and stuff like that is the donor and source star. So in this case, for a dwarf nova, it's a white dwarf star with a sun-like star. And here we have some that I think are dwarf nova, mostly because they are routinely getting bright. I can't think of anything else that gets bright on this type of timescale with this type of periodicity. You can see they kind of look like upside down eclipsing binaries, which is what I call them in my folder. Probably not very professional, but hey ho. But yeah, these are pretty cool. I quite like these. Here's another one. You can see. Also, you might be noticing the difference in sampling for a lot of these. We have quite a lot of measurements, but then this one we have a lot of measurements. That generally means that it's closer to the bulge, just the way the VVV works. There's a lot more measurements there. But yeah, pretty nifty. Again, probably a dwarf nova. We don't know. This is kind of the coolest part about VVV. There's just so much to do. Certainly surpasses my PhD. And here's a really, really nifty one that looks incredibly binary. I showed this to a bunch of people, and they are all like, I have no idea what that is. I couldn't possibly tell. We suspect it might be a dwarf nova because it does it once every 18 days, and that's about right for a dwarf nova, but who knows. Symbiotic variable stars, again, these are a lot like cataclysmic variables. These are basically just a type of star that is also emitting matter onto another star, and we get weirdnesses like this. This one, again, mega weird because it gets dim and then gets bright a little bit and then dim again and then somehow ends up back up there. We think it's real. I've shown it to a bunch of people. I've been in talks with a guy in Poland about this, and he's as perplexed as I am, as everyone is. But I hope I'm kind of making the case that VVV is an incredibly unique data set with a lot of really cool stuff in it. And gravitational microlensing. Matt has just talked about gravitational lensing. This can also happen on the star basis. So we have a lot of stars that are moving in the Milky Way. So if a star happens to get in front of another star, we can have these very tiny microlensing events. And here you can see some of those here. Don't know why my code found those and thought they were cool, but it did. And you can see just gets brighter and dimmer. This could be a flaring event, but if it was a flaring event, i.e. something being ejected onto the star or something to make it go brighter for another reason, it would probably not be symmetric. But the fact that it's symmetric to me makes me think it's probably a microlensing event. Again, none of these are confirmed. A lot of these, you are the first people to see these light curves. I probably should have told my supervisor before I did this. He might be mad, but hey ho. Pretty cool though. Again, more just incredibly unique things that are really interesting. I Googled star, and this is what Google gave me. I thought that one's really cool. And these are the ones that I have absolutely no idea. No idea. And the reason I think these are real is because I found 3 of them that all look very similar. Something's making this get brighter, and then it's not, but you would think it'd be maybe sinusoidal, but it's like a hump and then a flat part and then another hump. I honestly have no idea. I wanted to put these in because I really like them, but I can't give you any nice scientific commentary on them other than, look at that, that's cool. And there's a few of those. And I'm going to leave you on my incredibly information-dense poster that I presented at a conference because I didn't have any other thing to leave here. And there's about a gajillion more slides after this that I had to delete because they were too nerdy. So thank you very much.
What's it all about? Have you got, you've got a load of kind of really weird looking light curves. The Americans, when they got this with some of the Kepler stuff, they gave them like cool names like tweakers and flippers and dippers. Yeah. You're going to start giving them cool names?
I found a lot of these after Callum submitted his paper on the discovery of the new star. We realized how incredibly hard it is to name something cool things like that. Because we think this might be, was it a redback? Or a black widow or some other really cool name? So yeah, it's a black widow, that was it. Yeah, because it said, yeah, anyway. So maybe this has already got a cool name.
I mean, don't do it in the paper, do it on Twitter or something.
Oh, yeah, okay, yeah, yes. The wibbly wobbly stars, like that one I like.
Okay, firstly, that last slide, I think it should be a camel star because I love the double hump.
Yeah, oh, I like that. Yeah, okay, yeah, I see it, yeah, I like that, that's cool.
But the other one is, given the sort of we have no idea thing, what's your favourite crazy theory for any star, not just that one?
I mean, I could do the easy one and say that's aliens, right? You know, who knows? That makes no sense to me. I don't see how it could possibly get bright in that short a time. So aliens.
Thank you very much.
Well, thank you very much.
One quick one.
your crazy star thing is on. Your crazy star thing, that couldn't be 3 stars, could it?
Ooh, yeah. So that was one of the things I was thinking. Is this like a binary star where one of the stars is incredibly variable, and we're seeing the variability of one of the stars and also the binary part of it? Could be.
The 3rd star.
Yeah, okay, yeah. I mean, they don't typically last that long is the thing, because of the fact that it's a chaotic system. But honestly, your guess is as good as mine for this. I have no idea. Exactly, yeah.
You don't tend to get 3 stars that are close
It would be like a contact binary. And then another, but that, I mean, maybe. That's what I'm saying about the uncertainty there.
Sorry, I'm interrupting.
No, yeah. Well, thank you very much again. Don't need to. Oh, I got 2.
Yep. Okay. So we'll thank all 4 speakers again quickly, and then I'll hand over to Jerry.
Thank you very much, Ben, and of course for the speakers. But Ben arranged them all and did a very good job of doing so. I mean, if we had said at the previous meeting, the next meeting is going to have 4 speakers at PhD level talking about their research, we wouldn't have had this many people here, I suspect, in the audience. But I'm sure that you're all pleased that you did come along. I certainly am. It's been quite something to listen to this range of work, and it's, I think, an excellent example of why the University of Hertfordshire has such a high reputation with regard to astronomy. And it's because of that that we are so pleased to be associated with the university. We've been attending their open evenings at Bayfordbury Observatory for quite some time now. And of course, I'd be remiss if I didn't mention that the next one is coming up this coming Friday. I don't know if there are any spaces left, but week Friday, sorry. We shall be there, of course. And you have another one, I believe the 24th of March, is it? Yeah. One in February and 24th of March. And we shall be at those. And then on Saturday, the 25th of March, we are planning to hold our next open event ourselves, our next outreach event, which is to help people with telescopes. We always say that it doesn't matter how much a telescope costs, whether it was £60 from Lidl or something with a couple of extra noughts on the end, if it just stays in the loft or somewhere else and isn't being used. Some people have problems using their telescope because they're just not sure how to go about it. So we have a session where we will be explaining how telescopes work, how to get the best out of them. It's actually called My Telescope Doesn't Work, because of course you always blame the equipment, it's never your fault. And so look out on our website for detail about that. Now, apart from that and our other main meetings here, we have a joining group which is to do with astrophotography, and we do have some absolutely incredible astrophotographers in the society, Steve here being one of them. But Dennis, all right, well, Alan will tell us something about forthcoming HAGAS meetings, which are free for Hertford Astronomy Group members. So I'm now going to hand back to Alan, who's going to finish off the meeting for us, I believe.
Okay, well, thank you very much indeed for what a fantastic evening that's been. I'd like to especially thank Callum, Shravya, Matt and Niall for this brilliant evening. Presentations have been outstanding. we know that to prepare them takes ages, and we are truly thankful for all the work that's gone into them. The people out here on Zoom have been absolutely amazed by it, as I'm sure those of you down in the university have been as well. So thank you again. And particular thanks to Ben, because not only did he get the students to volunteer to do this, but he's done an awful lot of work for us in being letting us use these lecture theatres down here in the Lindop building. And of course, as Jerry had said earlier, we thank him for letting us come along to Bayfordbury. It's a great place to come along on the open evenings and meet new people. Maybe that's where we met some of you originally. So Ben, thank you very much on behalf of the Hertford Astronomy Group. We really do appreciate all that you've done for us. There are notices about the next coming meetings on our website, so do go along there. But our next main meeting is on February the 8th at 8 o'clock. And again, we're going to Zoom and live. And we've got Francisco Diego coming along to talk to us on Paradise Planet Earth, a human responsibility. We'd be delighted to see you all there, particularly our speakers who came this evening. If you want to come and join us, we'd be very pleased to see you at that meeting. So I think that's all we've got to do, is to say thank you to all of you for coming along, the audience. Without an audience, there's not much point in us doing it. But a special thank you to all the team behind the committee who have worked tirelessly to make these presentations as smooth as possible. No easy task. It goes all the way from the admissions process, ticketing, the technology side of things, and the organising of meetings throughout the year. We're a great team. We work together very well, and it's a chance to say thank you to all of those. Other than that, if you're down at the university, please have a safe journey home. And those of you on Zoom, if you want to stay around for a little bit longer and have a chat, by all means do. Otherwise, we'll see you all on February the 8th. Thank you.